quite close. And we wanted to find the total angle traversed by this planet from the time of closest approach. Well, it doesn't look so. This is supposed to be closer than this. From the point of closest approach to the Sun to the point of farthest recession from the Sun. And then twice that, of course, would be the total angle traversed from perihelion, the closest place to the Sun, to the next perihelion. Okay, and so we had found an equation which said that du d phi being the angle. Let's see if I can remember the definition. So we had this was defined, the setup here was that the R0 was the Schwarzschild radius of the Sun, and we were using a variable, R, dimensionless variable, R0 over R, instead of the radius itself. And then we found, in terms of that variable, we had found that du d phi squared was equal to f of u, which was equal to, in this case, u minus a times, I guess, b minus u times 1 minus a minus b minus u. This was all under the approximation that u was much less, or not yet, but it will be in a second, under the approximation that u is very small. In other words, that the planet, or this point test particle, as we're idealizing it, is much farther than 1 Schwarzschild radius away from the center, which of course it is in the case of the solar system. So I think that's it. So then we just, and then A, of course, as you can see here, f of u, if we drew a picture of it, must have had a picture. Yeah, f of u looked something like and then it was doing some other stuff. The important thing is that the minimum value of u, which means the maximum value of the radius, we called A. Of course, this f of u, from this equation, f of u must be positive. When it goes to 0, then the speed of approach or advance to the Sun goes to 0, so that's the turning point, one of these two turning points, perihelion or aphelion. Aphelion or aphelion, I don't actually know how to pronounce the word, but so that's A and B. And then so the answer will be in terms of those two distances. And then this is the way the polynomial had to be. So all we have to do then is to evaluate the integral so this is half angle. Let's call it phi over 2. Total phi meaning the total angle is the integral from a to b of du. Just looking at this, it's the integral from a to b of d phi, which is equal to the integral from a to b of du over the square root of f of u, right? Which means that's the integral. This is, I think, where we stopped, integral from a to b of du over the square root of this thing, u minus a times b minus u times 1 minus a minus b. Right? So that's the integral we have to do. If we knew a and b, I mean, you could stop here if you know a and b, measure it. This will give you, and then double this integral, that'll give you the total angle. Okay. So that, but it's convenient. So that's basically the story. You could work out what this is for the Mercury, for example. But it's convenient to put this in a slightly simpler form that's available when we know that u and a and b, all of them, when we know basically that u over its whole range is much less than 1, then we can approximate this. We can get a sense of the order of magnitude of the deviation from the flat space, the Newtonian answer. So if we approximate this, it's approximately equal to, so keep this and then expand out the square root of this 1 minus a small term, and it will then be integral from a to b again of du over the square root of u minus a times b minus u. The point is we can do this integral, and then we just have to multiply it by 1 plus a plus b plus u over 2, right? And that'll then split. So u is much less than equal 1. So that also means, of course, that a and b are very small. They're just the extreme values of u. Okay. So this reduces us to doing basically two integrals. One is this multiplied by 1 plus a constant, 1 plus a plus b over 2. And then the other one, the integral with the u in it. Now this one, if you think about it, this one has to be pi, because if we go to the Newtonian, because of what we know about, in a sense we're rederiving the Keplerian orbits, but if you know already about it, then you know this better be pi, because you know that in the limit when these go to 0, where the Schwarzschild radius goes to 0, that you do have a closed orbit, and so in one from perihelion to aphelion, it goes exactly pi. So we know in advance what this should be, but then we have, so this will equal, anyway, in any case, this is equal to 1 plus a plus b over 2 times this integral from a to b of du over the square root of u minus a times b minus u, plus, and then what's left over, the same integral of u du over the same square root u minus a times b minus u. Squeeze another one in. So for this one, to see that this is pi, let's make the substitute. This is basically just strictly a parabola. So just makes the substitution that it's sort of centered on a plus b over 2. So make the substitution that u is that plus some variable x. And then I'll also introduce a new constant c, which is b minus a over 2. And in that case, u minus a, this square root thing under the square root, u minus a times b minus u will just be c squared minus x squared. You can easily check. Then the integral becomes, then we're left with this integral that would just look like the du over the square root of u. That becomes the integral from minus c to c. Now we just made the domain of integration be sort of even around the origin. So it becomes the integral from minus c to c of the integral dx over c squared minus x squared, which you can, of course, actually what I didn't think to do is give this first integral to Maple or Mathematica. I don't know what it would. Does anyone have a, you can check. I don't know. I suspect it, what? The very first, the top one, yeah. I don't know what it'll give some, either I guess it either won't do it or give some obscure special function. But anyway, this one it can certainly do, and this one is just the arc sine of x over c evaluated between x equals c and x equals minus c, and that's pi over 2, twice pi over, each contribution is pi over 2. So it equals pi, as we knew it had to be. The other integral that we need is the integral du, u times u over the square root of c squared of this object, u minus a times v minus u. Again, making the same substitution, it becomes the integral from minus c to c. Oops. What am I doing here? Yeah, it becomes, why do I have a half here? Oh, there was a half. Did I leave something out here? There was supposed to be a half here, right? Inherited from the line above. So there's supposed to be a half, and then that's, if we make the same substitution, then the u becomes a plus b over 2 plus x times dx, and then over the square root of c squared minus x squared, which is, okay, so then part of it is the integral we already did before, this constant, so that's a plus b over 4, pulling that out, times the same integral of dx over the square root of blah, blah, blah. And then the other part that's left over is 1/2 the integral. We have x dx over the square root of c squared minus x squared, but that's 0 because it's from minus c to c, and this is an odd integrand, right? So what we're left with is just a plus b over, so it equals a plus b over 4 times whatever we got for that integral, which was pi. Okay. So therefore, putting the whole thing together, if I did it right, the whole on the board, the integral from u equals a to b of d phi then equals, so what do we got? 1 plus a plus b over 2 from here times the square root times this integral, which was pi, plus 1 plus this other integral. I think I left out the 1/2 here, right? No, here I think I left out the half. Yeah. So plus whatever is left over there, which is a plus b over 4 times pi. So it's equal to pi plus 3/4 a plus b times pi, I guess. Okay. So therefore the total, remember that was half the angle. So the total angle is 2 pi plus 3/2 3 pi over 2 times a plus b, which is equal to, well, this was all approximate under the neglecting the higher order terms in u. That's equal to then 3 pi is equal, so it's 2, so this total minus 2 pi, which is this precession amount of the precession, or whatever the opposite of precession is equal to 3 pi over 2. Now I put back what is a was r. So a is now, remember, a is equal to u, the smallest u. So it's the smallest value of, remember, u is r naught over r. So it's r naught over the largest value that r takes on. So I'll call that r plus. and so we get R naught times 1 over R plus 1 over R minus, where R naught, mind you, to relate it to the mass of the sun, R naught was equal to kappa m over 4 pi, or if you like 4 pi c squared, which is also equal to 2, kappa, remember, is 8 pi g, so it's, or if you like, it's 2 gm over c squared. So that's the definition of R naught in terms of the mass of the sun, or the center, whatever it is. So that's the answer. Okay. In terms of the Schwarzschild radius. So did mathematically, did you try?
It declined to evaluate the
integral. It says I declined.
Well, it was Wolfram alpha, so it just timed out.
It timed out, I see.
I
see. Oh, buy something. Okay. So that's the first result on the precession. So as you see, it's positive, so it is actually a precession rather than the opposite, an anti-precession, whatever that's called. So any questions on that? Okay. Now we want to go back and do the same thing for light. And that is, so let me recall the equation we had before we had this equation that you see at the top. Where were these A? I mean, where did this? I mean, there's a certain trickery involved in the way I did it. I didn't actually ever have to tell you what A and B were. Well, because we wrote the answer in terms of A and B, which is reasonable, because those are the things that you would observe about the planet. So, but let's go back to the equation that would have told us. So du d phi, remember this was, we had, just before that we had this equation, du d phi squared plus p of u equals E R naught over J squared. I think I called this, where P of U was equal to, what was it? The full expression. Let's see if I can. Oh, we already found this before. So in the massless case, I don't have to rederive it. So in the massless case, we found that P of U was equal to U squared over 1 minus U. Otherwise, it had another contribution, something that I called A squared, which was involving A squared, which was basically 1 over the angular momentum per unit mass. But since so it was the opposite, the reciprocal of that. So it was the mass per unit angular momentum. And since the mass is 0, that contribution goes away, and you're just left with this. So, and I think I gave a name. Oh yeah. So now we want to play a similar trick, and we want to express the answer not in terms of these quantities, energy. So the mass, of course, is gone, but there's still this term of the energy, ratio of the energy to the angular momentum. But instead of expressing the answer in terms of that, let's express it in terms of some more immediately observable geometrical quantity, which is the so-called impact parameter. So the picture is now that we have, let's see, if we want it to circulate in a positive direction, I guess I should have it going around like this. So we want, now we have a ray of light coming in, and then it goes something or other, and it goes out at a certain angle. The angle, again, this time we'll compute the angle from infinity to infinity, that is from u equals 0 back to u equals 0. So again, it'll be twice the angle from maximum value to minimum value of u to maximum value of u. Before we expressed it in terms of the minimum and maximum distances of the planet from the sun, now we want to express it in terms of what's called the impact parameter, which is, if you idealize this as being flat space and you just extended this as a straight line, well, no, I don't want to quite do it like that. Well, yeah, so if you imagine that the sun did not bend the light, then there'd be a certain distance between the ingoing and between the center and the trajectory of the photon when it came closest. So again, this is the distance at closest approach if if it was not bent. In the approximation that we'll work in, again, where u is much less than 1, the bending is very small, so it'll be a higher order correction if you want to replace this by the actual distance to the minimum. Okay. So that's the impact, so-called impact parameter. That is normally, for some reason, called B. So now what do we have? So in terms of the impact parameter, we can identify what these objects are. So first of all, what is the energy? So let P be the momentum of the photon. So measured far away, so we're basically in flat space. So I just mean the spatial momentum, the magnitude of the spatial momentum. So in that case, what is its energy? Something everyone knows from special relativity, right? So if it's a photon, a massless particle, so if it has, PC, or since we're setting c equal to 1, it's just equal to p. And what about the angular momentum? Well, angular momentum, it's conceivable you actually never saw this in special relativity, I'm not sure. But if you did, you would know the answer. And if you didn't, you still know the answer because you saw it in whatever, classical mechanics or something, right? So given the momentum, what's of this thing? What would be its angular momentum? That would be, yeah.
Would it just be PBI?
Yes, exactly. Yeah, it's just the same formula that you had. If it's not familiar, if you are worried that this might not work in special relativity, then you have to go back and work out what are the conserved quantities associated with the rotational killing vector. So that's a nice exercise to do, and you'll see that you get exactly the same result. Okay. If you remember, in other words, this is what we would have called zeta. I think zeta 1 to a PA, P being the form momentum. That was our J, and the other one, E, was minus what I called C, the time-like killing vector, PA, right? Just to remind you. So if you can work these out, but this is the standard formula. The pre-relativistic formula is still correct. So we can plug those in, and then we can relate these to the impact parameter. So it follows from these two equations that E over J, which is what we see in this right-hand side here, is in fact nothing but 1 over the impact parameter. So this whole thing, E R naught over J, is just R naught over B, which we would have called I guess I would have called it, this is the closest approach, so it's the largest value. So it's of u, which is sort of u max. Right? So now that it's all reduced again to an integral like that, so we get what it was p of u. So let's rewrite this. So du d phi squared plus u squared times 1 minus u equals r naught over b squared, or du d phi squared is equal to r naught minus this plus r naught over b squared. Again, it's just some polynomial. So this is, we could call this f of u again, where in this case f of u is given by r naught over b squared minus u squared plus u cubed. Okay, and so we have to evaluate again the exact answer, exact within the approximations that we made, which is the definition of b basically, and all the other approximations that are implicit in point particles and so on. Within those approximations, we get that d phi is equal to du over the square root of r naught over b squared minus u squared plus u cubed. Now it's just like before. What did we have? We had, where did the, there it is, yeah. So it's like, it's the analog of that expression, but it's a slightly different one. Again, it's probably not doable in closed form, but again, if we notice that u, if we remember that u is very small, again, it's not so small here, I suppose, because the light of interest is passing fairly close to the sun. Nevertheless, the Schwarzschild radius is something deep inside the sun, and I don't actually know what. Does anyone know the radius of the sun? 3,000? 3,000. Radius of the sun is? Oh, the Schwarzschild radius. No, but does anyone know the actual radius of the sun? The actual radius of the sun is more like 3 kilometers. Not 3,000.
Shouldn't it be the other way around?
Which other way around?
The Schwarzschild radius is 3,000 kilometers.
No, I didn't say that. The Schwarzschild radius is much smaller. It's just a few kilometers. But I'm asking what's the actual radius of the sun. I don't know what it is. Anyway, let's say it's 3,000. I'm sure it's much more than that, because that's like the radius. That's comparable to the Earth's, or not even the Earth's size. So it's at least 1,000 times smaller. So even a ray of light, even grazing the limb of the sun, one solar unit, one solar, one solar ray.
That would be about 700,000 kilometers.
Okay, so we have about at least 100,000. So this u is smaller than 100,000 anyway. So u cubed, so the point is that u cubed is then much, much smaller than u squared. And we can again make an approximation in which we expand it out in that way. So what did I want to do? So let's again put this square root, so we'll do a similar trick, slightly different. So let's put this square root in the form of a polynomial, so of a quadratic polynomial. So if I define a new quantity, y squared, to equal this thing here, u squared minus u cubed, then we can say that we're dealing with the integral. Well, and then we have that u squared. If we solve for this, then u squared is equal to y squared plus u cubed. But you see, u is very small, so this says that y is approximately equal to q. So this is approximately equal to y squared plus y cubed, right? Because u is approximately equal to y. This u squared is, therefore u cubed is approximately equal to y cubed. So u squared is approximately equal to y squared plus y cubed. So I've approximately solved for u in terms of y, and then I can just, under that approximation, I can just write down what is u, which is again, approximately equal to the square root of y squared, which is y, plus y cubed over 2 twice the square root of y squared, just approximating a square root, which is therefore approximately, in fact, exactly equal to y plus y squared over 2. So I can make that substitution approximately, and then it implies that du is also approximately equal to just varying that, du is approximately equal to u times y, du is approximately to dy times 1 plus y. So making those substitutions, we get so the half angle, again, so just the angle from, this is half angle, from infinity to closest approach, perihelion, I guess you could call it still, is will be the integral from 0, u equals 0, which means infinite distance, r equals infinity, to, now I've given it a name, u naught, Gesundheit. It's given to u naught, I could have called it u naught before, is du over this square root, and now we've written it in terms of y, so it's the integral from y equals 0. Of course, when u equals 0, of course, y is also given this definition, when u equals 0. Y is equal to 0, so it's the integral from y equals 0 to what I'll call a, meaning just whatever the maximum value is, of dy times 1 plus y, that was our du, divided by, and then we arrange this, oh, sorry, I shouldn't, so this a was defined by, where did it go to? Anyone see an A here? Maybe I just introduced A. I thought, well, I just didn't write it. So we made this definition here, and the point, when you make this definition here, and A was R naught over B, obviously. So I need a few more definitions I forgot to make. I guess A must be R naught over B. And then, is that written here? So, yeah, I should have said that. A is defined to be R naught over B. That's my minimum, that's the closest approach expressed in terms of y. And then also a squared minus y squared. Well, we defined y squared to be u squared minus u cubed. So a squared minus y squared is just, r naught over b squared minus u squared minus u cubed. In other words, the whole substitution was just designed so under the square root you would see a squared minus y squared. So that's equal to r naught over b squared minus u squared. I think, was it plus u cubed? I should have written that before. Okay. So that's the substitution, and then this then takes on this is two terms as before. One is the integral from 0 to a dy over the square root of a squared minus y squared, and then the correction term, which is the integral from 0 to a of y dy over the square root of a squared minus y squared. But we saw both of these integrals just before. This one is equal to pi, and this one, did we see this integral before? Maybe we didn't quite see it before. We saw something very... Oh, this is from 0 to a. So we have to do this integral. So this is a different integral, yeah. But this we can do because you can just make a substitution. You know, you can make a new substitution. X is y squared over 2 or something like that. And this is just a trivial integral to do. I won't bother with 2 or 3 lines detail. This equals 2a. The first one is supposed to be pi. Yeah. Oh, you're right. You're right. It should be pi over 2. Absolutely. I haven't yet multiplied through it. Yeah. Thanks, man. Therefore, this integral probably doesn't have the 2 either. Now I multiply by 2, so the angle is equal to pi plus 2a, which is pi plus twice r naught over b. So that's the answer. So the deflection is this. So is equal to r naught over twice r naught over b. So that's the other answer. So these two classic tests. One was the precession, that's the result for this, and the deflection of light, bending of light about the sun is given by this. Okay, so it's very small, obviously, as we just noticed, because it's what we said, 100,000. Anyway, it's a tiny thing, but anyway, it's now. It's certainly possible to measure it fairly well. I don't know the precision. I think when it was first measured, the precision was very poor, and it was almost maybe not quite really possible to distinguish it from the Newtonian answer, which turns out to be half of this. So if you imagine that light was just if you forgot about relativity and imagined that light was just a particle moving at just some particle like any other moving at the speed of light, you could work out its Keplerian orbit, and you could work out the deflection of that, and it turns out that it's half this amount of the deflection. It's interesting to go back and see where the difference came from. You can do that using Fermat's, when we discussed, if you remember Fermat's principle, you see that, I won't bother going through it now, but just to save time, but it's interesting to do. I was going to make it a homework problem, but I don't think we'll have time to make it a homework problem. So it's interesting. You see that there's really two sources of the bending. One is due to the time, whatever it's called, redshift, the gravitational redshift or time dilation associated with gravity, and that's basically this Newtonian one. It's just as if if light slows down when it approaches the sun. Maybe I'll draw a picture for that. So if light, I think I had this picture before. So if you imagine a wave packet, and then light slows down, then the inner part of it slows down more when you're nearer the sun. So it's a varying refractive index, so to speak, and that causes bending, just like any varying refractive index does. And that involves the Newtonian potential precisely because, remember, the redshift is given in the linear approximation by the Newtonian potential. But then there's another effect, which is that the geometry in the neighborhood of the sun is distorted. Distances get longer, times get shorter, distances get longer in the standard coordinates. And that makes it a little bit unfavorable to go near because remember, Fermat's principle says that the time, you should get there in the shortest time. So if you want to get here in a short time, you should stay a little bit away from the sun because the distance, you don't have to go as far. The distance is shorter. And so that causes another bending, and they turn out to be equal. So the only difference between relativity and the Newtonian result is actually this effect from the distortion from the curvature of space in the neighborhood of the sun. The curvature of time, so to speak, the redshift is not really it's not really a new effect in some sense. Okay, so I think anyway, those are the two formulas we were after. So now I think we can go on to the next chapter, so to speak, which is heading towards the Einstein-Hilbert action principle, that is, so that we can derive the Einstein equations. But for that, we have to first discuss, we have to construct the relevant quantities, namely all those based on the curvature tensor or the Riemann tensor. So that's next, but yeah, so any questions on this? Yes?
I'm just trying to make sure I understand what the impact parameter means here.
Oh.
So, are we just imagining that the sun's sort of gravitational mass just gets cranked to zero and we watch the path straighten out and then measure the distance to?
Yeah, I think, or you can just take it, if you like, just take it to be the minimum. I could have just as well defined it to be the the perihelion or whatever, the distance of minimum approach. I could just, because, I mean, of course, this is really exaggerated. If you actually drew the picture, you wouldn't see the deflection at all. It's 1 part in 100,000 or whatever we found. So we could also just take it to, if you want a more straightforward definition, this is also B, the distance from the center to the closest approach. Oh, again, the curvature is so slight that no, it's not the I mean, if you want to know exactly what it is, so it's in the standard spatial coordinates. That's right, because that's how I defined it exactly. Yeah. But in practice, these will produce higher order corrections. But in practice, you just look at the sun, you see where the image of the star is, and you just measure its distance. And you try and get it as close to the limb of the sun as possible. So it's basically just going to be in the actual application. It's just going to be the radius of the sun, basically. And the sun is not a neutron star or anything like that. The space-time inside the sun is pretty nearly flat. So the you have to. It's not entirely obvious, I suppose, but the Schwarzschild radius in that situation, the radius measured in the Schwarzschild coordinate will coincide with the sort of flat space radius. Because one way of seeing why that is that the radius, if you go back to the formula for the Schwarzschild metric, well, something over that. But the important thing now is this r squared d omega squared. So it means that so first of all, these numbers are very small. So the correction to the flat metric is very small. So that's the most obvious thing. So we can more or less use the flat space-time. But also this has an invariant definition as long as we have spherical symmetry. This r squared basically is giving you the area of the sphere. So the area of some 2 sphere of a constant radius is equal to 4 pi r squared. And that's an exact statement if you use the Schwarzschild coordinates. That's one way of thinking about what the coordinate r means. Okay. So any other questions on our discussion of motion and the Schwarzschild metric, or just in general, the conserved quantities and all this? Yeah.
Yeah, another question going back all the way back to when we were talking about killing vectors. I realized today that the 2-sphere, I guess, has 3 killing vectors, even though like the tangent space at any point is 2-dimensional. I thought that was weird.
It is a little bit. I agree with you.
So, I mean,
How can it be?
At no point did you say
How
that,
can there be?
The dimension of the manifold restricts how many killing vectors there should be, how many linearly independent killing vector fields there should be, but I mean, intuition would lead me to believe that there should be maximum.
Of 2, right. So how can it be that there's more linearly independent killing vectors than there are dimensions of the... Yeah.
Do you have any intuition there on like how better to think about this?
Well, you may or may not like this, but I mean, the answer is yes. So it's a question of the rotation group. I mean, a killing vector is just an infinitesimal rotation. So if you ask, so the rotation group is itself some sort of manifold, right? In fact, if you ask what manifold it is, it's what's called RP3, the projective three space. And so if you ask the dimension of this, I mean, and the killing vectors are infinitesimal rotations. So if the rotation group, well, since it is kind of a sphere, I can represent it. So this is SO3, the connected component of the identity in the rotation group. And here's the identity, usually called E or 1. Just that's somewhere here. And then in the infinitesimal neighborhood, just like any manifold, of the identity is a little approximately flat space, not a space-time now, but just a space, not a physical space, just some space. And its dimension, of course, is equal to the number of linearly independent killing vectors, because the killing vectors are the infinitesimal rotations. So there should be as many linearly independent killing vectors as there are dimensions of the group. Now we can ask, what is the dimensionality of the group SO3? And you know, well, then, so how would you figure it out? There's many ways to think about it. But we know it's a three-dimensional group. And one way to see that it's a three-dimensional group is to say, how many parameters does it take to fully specify a rotation? So we know that this is in Euclidean 3 space. Of course, it's different in higher dimensions. But in Euclidean 3 space, to specify a rotation, we know that you can do it by giving the axis of the rotation and the sort of angle through which you do the rotation, right? So that's some deep, if you like, fact about Euclidean space, that the most general isometry that fixes a point, the origin, has that form. And so what's the axis? I mean, the axis, that's a direction, so that's given by 2 angles, right? The angles on the sphere, unit sphere, and then a rotation is amount, an angle of rotation. So that's a third parameter. So it takes obviously 3 parameters to specify an element, a group element of SO3. So it is a three-dimensional, so it should have 3 linearly independent. Now you go back, but nevertheless, how can it be that in 2 dimensions there's more than 3 linearly independent vectors? So of course the answer is there aren't at any given point. It's the vector fields, and so the vector fields are not constant. So then even though at any given point you can write the third one as a linear combination of the first 2, at some other point you can write it as a linear combination again, but it's a different linear combination. So it's a...
Okay, so I mean, if you take a manifold, you think about some, I guess, global symmetry, a group that's a symmetry group of the manifold as a whole, and that's how you work it out for the sphere case. I mean, I guess is it the case for like a general manifold, if it's going to have killing vectors that correspond to some global symmetry group?
By definition, yeah.
Okay.
Well, yeah, okay. But, I mean, yes. The reason I hesitated is the manifold could have, if it's an infinite manifold, then it can be that you can't actually exponentiate the vector field. This happens with the conformal group, for example, in space-time, where that's a 15-dimensional group, as you might know. So we have, from the Poincare group, which is the isometry group, we have 10 dimensions, which you can think of as 4 components of linear momentum and 6 components of relativistic angular momentum. But then there's another 5. Then there's another obvious one, which is just an overall scaling, which doesn't perturb the light cones, and therefore is a conformal transfer. It preserves the conformal metric. And then there's another 4 that are less obvious. But those are not, they actually can't be realized globally because they introduce singularities. They could only be realized in some sort of conformal completion of R4 or something like that. So there's a subtlety there. What's happening is that those vector fields are blowing up as you approach infinity. And you can't even follow, if you try to follow them even a very small but finite parameter distance, at some place you'll run off to infinity. Where depends on which. Did I say this right? It sounds right as I say it, but something seems anyway. It's the case that you cannot exponentiate it, right? So if you ask what are the global conformal isometries of Minkowski space, 4-dimensional, meaning transformations which take Minkowski space points 1 to 1 into themselves and preserve the light cone structure, that is, preserve the metric up to a local conformal factor, then you'd only really have the Poincare group and the dilations or the homotheties. There's just the scale transformation. The others aren't there globally because of they are, except for a singularity. So basically, yes. So a good example of that would be, for example, the torus. These kind of examples come up in cosmology. If we take the torus, so let's take R2 mod Z2 mod Z squared. So I just mean to mod it out by translations. It's just flat space with periodic identifications, a 2-dimensional box, as we usually call it, periodic box. So locally, it's flat, right? It's everywhere flat locally. So you might think that it would have the same symmetries as flat space, which would be 2 translations and a rotation in the plane. But of course, it doesn't globally have those symmetries. It's broken by the topology in this case. It's not a question of singularities or something. It's just broken by the topology. So all you really have left is some sort of translations in this direction and translations. The rotations are broken by the global topological constraint. So when we talk about the killing vector, we're talking about a globally defined vector field. And so there wouldn't be a rotational killing vector in this. There's one, you could start out trying to, so the killing vector is, here, this would be quite a good killing vector. But this, if I try and build one like this, well, it's looking good up to a point, but then I find out here and here it's going the opposite direction. It just doesn't work. So it lacks killing vector. So what you say is true.
Is this related to why, when we discuss FLRW universes, that we never considered a torus cross R?
I don't know. We never considered it because that was just an illustration. So we weren't doing all cosmological cases. So that was just an illustration, and I worked with a sphere. The torus wouldn't admit a homogeneous. Let's see. It wouldn't be isotropic globally for exactly the reason that we just said. That's right. So why did I choose a sphere as a part? I could have chosen a torus.
Well, you listed the sphere.
If you want true isotropy, then you can't have a torus. That's right. If you want full isotropy. So that statement that I made was actually only, it was true if you demand perfect isotropy. It was a true statement. But you could easily say, who knows what's out, what I know is locally that we have this isotropy. In that case, you can have all of these 3 spaces admit identifications. You can take quotients of them, and they'll preserve the local isotropy. So a torus would be one of them. That would be taking flat space and making the identification. You can start with a sphere and make identifications, and you get. So for flat space, you don't get very much. I forget the answer. There's from topologically speaking, I think there's 8 possibilities that you can get by identifications. The torus is the most obvious one, if you want to make a compact manifold. Then for I think that's why I took the sphere, because I wanted it to be compact. so that the action would be finite. And then the full isotropy forces you to the sphere. Or you could actually do this antipodal identification, so you can produce what's called RP3, which is in fact the rotation group in another way. It's the same manifold. Yeah. So, but there are a whole bunch of other identifications you can make on the sphere. They produce very interesting topologies. People have looked for all of these. So far, they see no evidence, unfortunately. Looking out at the cosmos, looking for evidence of some periodicity in the space. And then from the other case, the negative curvature, the hyperbolic space, you can make even more identifications, so many that people have not even classified them yet, and it's not even known for sure whether they can be classified. Although I think the consensus, pretty strong consensus, is probably in principle they can. Unlike if you go to 4 manifolds, then in principle they're not classifiable. But the closed 4 manifolds, but the 3 manifolds, that's a whole long story which I won't try and reproduce now. But just if you want that local isotropy, there's still a lot of possible ways of forming identifications. So many that they're not even all known. And there's no reason really why we couldn't be living in one of those. However, it is true that they're not, as you said, they're not strictly speaking isotropic, and you might expect that to show up, because it wouldn't show up classically in the sense that there'd be nothing to stop you from having a matter distribution that would be compatible perfectly with local isotropy. But quantum mechanically, it's another story, because then you're doing sort of quantum field theory in that background, for example. And that quantum field theory it sees the anisotropy. So if you identified some natural vacuum state, like in a static space-time, that was just that space with its isotropy across time, then the vacuum would actually be anisotropic. Since a quantum state is a global object, it would actually be, in some tiny way, of course, but it would be anisotropic. And so, who knows, in the early universe when quantum gravity was important, it could have made a big effect. But no one really understands that too well. Any other questions? Okay, so next topic now is the sort of. So if you could go back and think what we've been doing, we started off discussing a situation where gravity, space-time, was dynamical, and in some sense matter wasn't dynamical because we just put dust, and dust hardly did any. It's dynamical in a kind of trivial sense. It was dynamical in the sense that it certainly contributed to the action, that certainly influenced the development of the cosmos, but it wasn't moving around, or it wasn't reacting to the space-time metric in a very interesting way, just in a trivial way. Then we've gone back and we've talked about situations where we treat the matter as test matter, and specifically particles, and understand how it reacts to the space-time metric and how you can use that to explore the space-time metric. But we ignored the back reaction. So we left out the dynamics of gravity in that more difficult case. Now, of course, we want to put the dynamics of gravity back in. And the first step to do that is to understand the dynamics of gravity alone before you put back in the matter. And then, of course, you want to put them all together. But the second and third steps are not all that different. What they both amount to is just finding a term. When we started, we wrote down the action principle that included the term for gravity in it and a term for matter. And now we've studied a lot more about the term for matter when matter is not just uniform dust. We have, at least when it's particles, we have an action principle for it. Now we have to now find the right term in the action for gravity, okay, which is called the Einstein-Hilbert action. And then, as I mentioned, you might think then you just have to add the two terms together and that's the story, but it's actually not consistent because point particles would have an infinite energy density and are not consistent in relativity. So when you really want to put them all together, you have to use a different model for matter, some sort of continuous matter, which we actually didn't study yet. But conceptually, the main thing we need now, if you ignore that difficulty, the main thing we need, which you shouldn't, of course, but I mean, it's not just it's not something that you can easily identify as being, I mean, since it's an infinite correction, it involves infinite renormalization in some sense. So, but if we ignore that, then all we need now is to have the term for gravity action more general than just the special homogeneous isotropic space-time that we started with. And when we started, of course, I just told you what the action was. I didn't show where it came from. So now we want to see what the general expression for the gravitational action is. And then, in particular, go back and check that I didn't lie to you when I told you what the action was for the Friedman, Robertson, Walker universe. Okay, so we might say that we're starting a new chapter, which is dynamics of gravity. And for this, you can read, again, in the textbook, there's some sections that deal with it. So in Wald's book, it's section 3.2, and in Bernard Schutz's book, it's section 6.5 to 6. Actually, what is it? 7, I think it says. 7, yeah. So the first order of business, of course, we can't just, I mean, everyone has probably seen what the action is up to a factor. I mean, if we set this kappa to 1, it's just the integral of r dv. We know that's what what we have to do is say what is meant by this r. So we have to define curvature and the curvature tensor. So that's the real first order of business. Also known as the Riemann tensor. Okay. So let's think about what that means. I mean, what it would take to, what we're trying to capture geometrically is, of course, curvature, right? So to think what that means, imagine a surface, go down a couple of dimensions and imagine some sort of surface, some curved surface embedded in 3 dimensions. So when we talk about its curvature, so this is obviously drawn not flat, but there's 2 kinds of curvature that one associates with it, which go by the name of extrinsic curvature and intrinsic curvature. Intrinsic curvature means because of most of our intuition is from this 3-dimensional case with a 2 surface embedded in it. And in that case, the 2 are so intimately related, it's a little bit hard at first to take on board that they're actually quite different in 4 dimensions. They're not at all that close. They're still related somehow, but not. But there is quite independent notions. What's called intrinsic curvature is that curvature that you could detect by knowing only the metric within that surface. So like the surface of the Earth is a surface in R3. And that's round, and we can test that it's round without even looking up. I mean, if you look up at stars and you see, however these people measured the size of the Earth, right? They went to Alexandria, or I forget where it was, but they found 2 cities that were, I guess, due north and south of each other, and then they looked at noon at what angle was the sun in one place and at what angle was the sun in the other place, and then knowing how far those places were, they were able to figure out radius of curvature of the Earth, and therefore the radius, or that is the radius of the Earth. So what they were doing is they were measuring the extrinsic curvature to the Earth. They were measuring, they went to 2 points, and they took the normal, they used the sun as a measurement, but basically what they were finding is looking up at the zenith in each place and seeing what angle separated those two zeniths as you get from one place on the Earth to the other place on the Earth. That's called extrinsic curvature. How does the normal to the surface move around as you move around on the surface? However, there's also intrinsic curvature, which we could do just even if it was cloudy all the time, like say in Waterloo, for example, and or Paris for that. Then you would, even so, you would be able to know that you're living on a curved surface. So you would draw these triangles of a certain size, and you'd see that the angles didn't add up to 180, and so on. They added up to more than 180, and you would get that's known as intrinsic curvature. So it's this one that we're talking about when we talk about the Riemann tensor. This is measuring the intrinsic curvature of some manifold space-time, which we don't particularly regard as embedded in any higher dimensional space, and certainly not any higher dimensional flat space.
You circled the wrong one?
What? Oh, I circled exactly, yes. So this is to be eliminated. Anyway, yes, I circled the wrong one. At some point I have to tell this joke, which you probably heard, so that I'll tell it now. The professor is thinking A, and he writes B. No, he's thinking A, he says B, he writes C, but the correct thing would have been D. So that's the way lectures go. So that's good. So I hope. Yes. So we want the intrinsic curvature, and that's measured by the Riemann tensor, which is represented by this. That's kind of what we're aiming at. But let's think a little more about the intuitive meaning of this and what it means for us in physics. So I think it has a straightforward, which we'll see in a second. Geometrical meaning is a kind of holonomy. It gives you the non-integrability of parallel transport around small loops, or even large loops, but the Riemann tensor corresponds to infinitesimal loops. So we saw before, when we talked about the Lie derivative, when we express it, I don't know if I made it too explicit, but we saw the formula for the Lie derivative represents well, scratch that. That was the case of D. Something could be said, but what I was about to say wasn't quite right. But in any case, this is right. So we can think of the Riemann tensor as a measure of the failure of parallel transport around to come back to itself around a small loop. It's quite analogous to the case of a gauge theory, where you transport, when there's a magnetic field and you transport electromagnetic phase around a small loop, it doesn't come back to itself. And you measure that, for example, you observe that in the Aharonov-Bohm effect. This other non-integrability we observe all the time in everyday life on the surface of the Earth also. There was...
Could you just define what you mean by non-integrability?
I will, yeah. But what I mean, I'll make it more precise, but what I mean is you take a vector, this is the intuitive meaning, you just take any vector at this point of the manifold, and you transport it, you carry it around this loop, always so that it's parallel transport. So it's always going parallel to itself with respect to the local, approximately what I called momentarily inertial frame. But we've defined parallel transport anyway. So you use parallel transport, you take it all the way around. When you come back, it may not be the same vector. It will, in general, not be the same vector. It will have to have the same length because parallel transport preserves the metric locally, so it preserves length in particular. And it preserves angle locally, but globally, it need not. length is a scalar, and therefore it's preserved. If it's preserved locally, it'll be preserved globally. But angle is not a scalar; it's a relative quantity, and so it's not. It will not. And if you want to see an example, the Earth is again the best practical example, or sort of most familiar example. But it's even easier if you think of a cone. You can see exactly what's going on. So imagine that you take a cone like this, and you take a vector on the cone, say this one, and you parallel transport it around the cone. Well, it'll come back not parallel to itself. And the way you can see that is to slit the cone somewhere and open it up and flatten it out, right? And then you'll have, it'll look something like this now. It's I could cut this out of paper and then glue these together, and I would make a cone, right? So, but now the flat metric is made explicit. The flatness of the metric is made explicit. In fact, when you look at a cone, you might say it's not flat at all. This is not a flat metric. That's because you're thinking about the extrinsic curvature. But intrinsically, it's flat, as we see now, because if you slit it and open it up, it'll lie flat on the blackboard. Okay, so now what will happen? I take this vector, I'll parallel transport it. It'll still be this vector, right? Because this is flat. But then when I glue them together, this vector will become that. It won't become this vector, right? Because these aren't parallel. Anyway, I don't see a great look of recognition on everyone's face. But if you think about it for a few minutes, you'll see that that's right. And this angle, which is called the defect angle of the cone, is precisely the non-integrability of parallel transport around on a circle that goes around the vertex of the cone. But everywhere else, if you go around a small circle, you'll come back to yourself. The vector will come back to itself. But if the circle links the vertex of the cone, then it'll actually change the angle. This, incidentally, this is the geometry around a string, like a cosmic string. If you just look at a two-dimensional cross-section. Yeah.
So the cone does have intrinsic curvature?
The cone has zero intrinsic curvature except at the vertex, where in some sense it has a delta function of intrinsic curvature. Right.
But I thought the idea of it going around a circle and not coming back to itself
is intrinsic curvature. Yes, and good point. I mean, that's right. And it does have intrinsic curvature. It's just localized at a point. It's kind of got a delta function worth of curvature. So you don't see it anywhere except if you link that point. But of course, the surface of the Earth is more typical, or more the kind of thing we're talking about in continuum physics, in classical relativity, which is that the curvature is distributed uniformly. So if to the extent that the Earth's surface is perfectly round, the curvature scalar, which is the measure of the size of the curvature, is the same everywhere on the Earth's surface. And so then you get a result. It's not topological like this. It's not just a yes, no, but you get a result that depends on the size of the loop. And in fact, what happens is you take a loop on the Earth's surface, then the amount by which the angle rotates is proportional to the area of the loop. That's the result. And again, there's one simple case where you can see it. I think we actually discussed this once before. Start at the north, take the Earth, start at the North Pole, take a vector. Well, let's take a vector pointing. It has only one way to point, south, but anyway. But take this particular south, and now parallel transport it around. So just walk south till you come to the equator. Now it's pointing. Now it is pointing, still south, of course. And now walk east, let's say, till you come to the other side of the Earth. It's still pointing like this, right? Now walk back north, carrying it along with you. Now it's pointing like this, right? So it rotated by pi. by going around that loop. And in this particular case, you can see if you just go halfway around, it'll rotate by pi over 2, and so on. If you just take these orange slices here, it'll obviously be, the amount of rotation will be proportional to the area of the slice. So that's a special case of this general fact that I was quoting before. Yeah?
So if we were to parallel transport along some sort of space-filling curve that has no area?
Well, it would be very... space filling curve. Let's see. Could you parallel transport along? I'm not sure that it's well defined to parallel transport along. Space filling curves are not differentiable. So if the curve has no well-defined tangent vector, I think if you worked, I mean, the definitions I gave will certainly fall on their face. But if you, when we define parallel transport, you might. Yeah, it's a good question. I am not sure what the answer. You might be able to come up with a local definition of what parallel transport means, even for non-smooth curves. But then we'd have the question of what is meant by the area enclosed, and whether or not that equality between the area enclosed and the failure, and the angle by which you rotated, would have any meaning. I don't know. So that's one. Let's make a little space here. That's one of the important consequences, or it is, if you like, the defining consequence of curvature. But for physical purposes, the most important consequence, I think, is what's called the geodesic deviation equation, which in another language is called tidal force. So this is how if you made the false statement, I was claiming that it was false, that many people do, that gravity is the result of curvature, then you would say that when the Riemann tensor was 0, there'd be no gravity. But that's, as we discussed a little bit right early on, like the first day or something, that's not really true, because on the Earth's surface there's no appreciable Riemann tensor. I mean, it's there, but it's very tiny, and it's much smaller in magnitude compared to what we call the gravitational field. What we're seeing there is really the mismatch between the local inertial frame and the motion of between local inertial motion and the motion of the surface of the Earth, which is accelerating. So what we call gravity in everyday life is not really curvature. It's really something to do with the relation of our reference frame to the local inertial reference frame. Meaning, and we express that in terms of these Christoffel symbols, if we use coordinates attached to our reference frame. So what we call gravity in everyday life is really more connected to the Christoffel symbol, which really means the failure of our world lines to be geodesic world lines. So it's the fact that d lambda, where u is our tangent vector, is not equal to 0, right? However, there is an effect of gravity. So you wouldn't see it, in other words, if you just went into a freely falling. If we jumped up and let ourselves be freely falling, we wouldn't feel gravity. But you would still feel something, and that's called the tidal force. And so what's really correct is that it's not that gravity, in the colloquial sense, is a consequence of space-time curvature, but that tidal force is the signal or the expression of space-time curvature. And the tidal force is something that means, for example, it's called tidal force because it's the effective force that makes the tides, of course. So what does that mean? It means, the Earth as a whole doesn't feel gravity of the sun because it's in free fall around the sun. It's undergoing geodesic motion on average, but not exactly. and that results in some. If the Earth was perfectly elastic and didn't have, and was more deformable than it actually is, then it would have some sort of elliptical shape rather than being round because of the tidal force from the sun. And that's shown. That's from a pre-relativistic point of view. That's saying you'd have to say, well, because gravity is a little weaker on one side of the Earth, it's near the sun, and it's a little stronger, and it's a little weaker on the side of the Earth, blah, 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 and you can work out the tides. But from the relativistic point of view, it's just that the sun produces a Riemann tensor in this neighborhood of the Earth, and that distorts the motion of the Earth. So that's what's called tidal force, and it's what the geodesic deviation equation expresses when you're talking about freely falling particles. So another example is if you take two particles. I mean, this is more literally an example of the geodesic deviation equation, because the fluid elements or particles making up the Earth, of course, don't follow geodesics because they're all exerting forces on each other. But if you just take two BBs or something and drop them in the neighborhood of the Earth, if you drop them, you'll see, of course, if you just drop them in rest, you'll see that they don't stay at the same distance from each other. They get closer to each other. Okay, because obviously they're both falling towards the center. So you might have, but why is that? I started them from at rest. They were at a fixed distance from each other. But as time goes on, if I draw a space-time diagram now, they started at rest, so they started moving parallel. But as time goes on, right, they converge, and that's, of course, due to the gravitational field of the Earth. But everything is local in relativity. So there's something about the geometry in the neighborhood of those two particles is bringing them together, and that's the Riemann curvature. That's the meaning of the geodesic deviation equation. So that's the other sort of, I think, main consequence. But now we just want to do some differential geometry, basically, some mathematics, and see how would we characterize what tensor quantity can we use to characterize curvature locally. So we're looking for a tensor to measure deviation from flatness, and of course intrinsic. So suppose that space-time were flat, then let me say one other thing. When we discussed the definition of parallel transport, we said that by a miracle in some sense, but it was a miracle that had to happen if the equivalence principle was to actually be viable. It was possible to match the flat metric not only at a point, but to first order in a neighborhood of a point. And then we use that to define parallel transport. But to second order, you can't match it. And so if you look at that inability to match it to second order, then you pick up the curvature. That's what we're trying to do now. So but if we were so let's see what that would mean. If we were in the flat situation, then we would know that these this covariant gradient operator would just be in Cartesian coordinates. It would just look like ordinary partial derivatives, and therefore it would commute with itself. Any two components of it would commute with each other, which would mean that if I write their commutator and let it act on any tensor field, I would get 0. Okay. However, in curved space, this will not be true, and the Riemann tensor will be precisely the measure of the failure of these two things to commute. Okay. And again, if you are familiar enough with gauge theories to get an intuition from them, certainly the U1 gauge theory, abelian gauge theory, then this is the analog of the gauge covariant derivatives failure to commute at a point. And you may know that if you commute two gauge covariant derivatives acting on a charged field, you'll get the magnetic field, or the space-time generalization, you'll get FAB by commuting two. Okay, that's just for those who are familiar with it. This is the gravitational analog of that fact. So using that, let's I could just start writing formulas now, but I want to relate that to what I said before, which was the failure of the parallel transport, more literally related to the failure of parallel transport to be integrable. In other words, this holonomy, this rotation, or more generally, this Lorentz transformation associated with going around a small loop in space-time. So I guess there'll just be time to set this up. So let's, just to make this fairly precise, let's introduce two vector fields, which I'll call eta c and eta, and imagine that they mesh, as we say. So we consider c like this, and eta like this. So this is c, this is the vector field. Oh, no, I got it backwards. This is c. I want to call this one eta, c and eta. And by they mesh, I mean if you go a certain parameter, I mean that their Lie derivative is 0. So, but this means, when I write this, I mean c bracket eta, which remember was defined as the Lie derivative of eta with respect to c, and it's also minus the Lie derivative of c with respect to eta. I assume that that equals 0. And that means that if you start here and go a fixed parameter distance, say parameter distance 1 along c, and then parameter distance 1 along eta, you get to the same place as if you did it in the opposite order. You go parameter distance 1 along eta, and then along c. So let's isolate this little square here, this parallel, whatever it is. Let's call this starting point O for origin, the point we reach by going a parameter distance. Of course, you have to think in infinitesimal now. So we go a parameter distance epsilon, let's say, and we think of c as an infinitesimal vector. We arrive at A, then we go a equal parameter distance from A along eta, we arrive at C, and then we can do it in the other order. Okay. And since we assume that they mesh, we arrive at the same point. So this is just setting up the problem. Now, if we could consistently transport the vector, we took any vector here, and we parallel transport it along this particular curve from O to A to C, and if parallel transport were integrable, meaning we're in flat space basically, or no curvature in this plane anyway, then we'd get the same result by taking it first to B and then to C. So if that were true, we could take this original vector V, let's call it VA, and we could get it using this mesh here. We could get it anywhere in space-time, or at least in this two-dimensional space we're looking at now. We could take it anywhere, and we'd spread V over the whole space. Is it clear? Because it doesn't matter which way we go. And then, had we done that, we would have guaranteed that when we go along the C direction, by construction, the parallel transport, it was parallel transported, so its covariant derivative along that direction would be 0, so I'm using a shorthand notation here. By this gradient sub C, I just mean CA grad A, the directional covariant derivative along the vector field C. And also, again, we could say the same thing for eta, again, because we've always done it in such a way that we could that it is parallel transported when we move along eta. So if there were no curvature, that is, if parallel transport were integrable, then we would be able to find a vector field V, which had both of these directional derivatives vanished. And that would imply then just trivially that grad C commuted with grad eta V would equal 0, because it's just it's just 0 minus 0 in this case, right? So V means here now a vector field. If we can't satisfy this, so in other words, if this is not actually 0, then this is a measure of the holomorph. This is a measure of curvature, or in this, I should better say, a measure of the holonomy, the non-trivial holonomy, the fact that you can't consistently parallel transport around every infinitesimal rectangle. So the idea is to use exactly this expression as a measure of curvature. So before doing that, I just want to make this statement a little more precise. I want to show exactly, this is not only a measure of holonomy, but it literally is. In other words, that this expression will give us the amount by which the vector V changes when you parallel transport it around this curve. Okay, so I claim, I guess we could probably start there next time. So let me just define a couple of things. So define this operator, which I'll call TO. How have I called it? TO, that's not a 0, it's an O. It's this origin here. TOA, let it map the tangent space to the manifolded A to the tangent space to the manifolded O by transport, by parallel transport. We defined this before. I forgot exactly what notation I used, but we discussed that concept before when we were talking about parallel transport. So it brings you back to O from A. It goes the opposite direction of the way the arrow points here, which that'll just be a convenient choice. So to say that parallel transport would be integrable would be just saying that if we apply TO, if we start at C, let's say, and we take some vector and we apply TAC to it, bringing it to A, and then we apply TOA, bringing it back to O, that in general, if it's integrable, that will be equal, but in general it will not equal the result of starting again at C, transporting it back to B, and then transporting it to O from B, right? And it's that mismatch which represents the holonomy. And so we'll see that we can directly relate this to, we'll see up to a factor of 1/2 or something, that's equal to, so this is effectively the holonomy element, the result of parallel transport around a loop, and we'll see that that's related to this covariant derivative acting on V, and we'll see, moreover, that although it looks like there are derivatives in V here, there actually are none. So it's just be a tensor acting contracted with V. And that tensor is called the Riemann tensor, and it represents, it's the local, it tells you everything that you need to know about the local intrinsic curvature, the intrinsic curvature at that point. Okay, so I guess I better quit at this point. Yeah.
So if we can find two vector fields that mesh everywhere, does that imply that the spacetime is flat?
Not only that they mesh everywhere, but that they're covariant constants. No. You can always find two vector fields that mesh everywhere. That's just like putting down a coordinate system on that. That's not a problem. The further thing is having found two vector fields that mesh everywhere. This talking about vector fields that mesh was only a technical device for being able to talk about this infinitesimal parallelogram. So what actually represents the flatness is that once we have them, then we can find a third vector field. In fact, we can find two linearly independent vector fields, really, if you want full flatness, which are covariant, which satisfy both of these equations. So then if you can do that, if you find two, I said because we're just dealing with the surface here. I should have really said four or whatever. So if you can find four, and then if you want real flatness, you have to take all possible surfaces, all possible infinitesimal loops and so on. But if you can find if you could find four linearly independent vectors such that you can spread them around by this device, making them be covariantly constant, then the space-time must be flat because you can use them to build a coordinate system. I mean, we'll see that maybe later. But it's the existence, it's these equations that represent the flatness, not the meshing. Any other questions? Okay, so we'll just carry on from here next time.